interesting, I feel. Trying to solve the game of Nim. Nim is basically a game where you basically take like out of a pile of matchsticks. Okay, maybe I should just type here. Out of a pile of matchsticks, you try to um, not be the last, not be the person to take the last stick. Okay, or maybe be the last person to take the last stick. Yeah, depends on how you want to play it. Okay, so this is basically trying to implement Monte Carlo Tree Search for a simple game just to illustrate how this works. We'll start with Monte Carlo, then Monte Carlo Tree Search. So maybe I just put a header here for Monte Carlo, and here will be Monte Carlo Tree Search. Okay, so I really like Monte Carlo methods, and AlphaGo, AlphaZero uses a variant of it with deep neural nets. Here we just do the Monte Carlo without the neural nets just to show like how good it can be already for simple games. Okay, so firstly we describe what is NIM. So NIM is you have n matchsticks. Each turn, player will to take from 1 to k matchsticks. Okay, player which takes the last matchstick wins, or rather I think the player who takes the last matchstick loses. Yeah, we should make it this way. Yeah, so this is the game of Nim. Okay, and then we code out the game here, I guess. Okay, so game coding. Okay, so we do a very simple game coding here just to see how this works. Okay, let me just save this. Okay, so we have a class nim. Okay, and then over here we define an init method. Okay, maybe we have like n and k over here. Uh, okay, so we have an init method with this self.turn, which is the player's turn. N is the total matchstick. K is the, so maybe we do a define a reset method also. Okay, self.matchsticks equals to self.n, the starting matchstick, and then self dot, actually that will be it, and then the turn becomes 0. Okay, so this resets the board, and then maybe we define a move. Okay, and then the move here will take in a variable like number. Okay, and then basically this move must be, okay, so if this number is smaller than k and greater than 0, and greater like that 1 to k, okay, then what we do is self dot n or self dot matchstick minus equals to num. Yeah, something like that. Yeah, so this one minus, and then what we do is, so this one is remove matchstick, and then this one will be to okay, else print invalid move. Okay, so over here this will be remove matchstick, and this one will be swap player's turn. Okay, so it's a very simple game. Yeah, it's just a game where you remove the matchstick and then you see who takes the last one. Okay, so after that we do a reset method when at the end of the game. Okay, so we also need to check whether win. Okay, so in order to know whether you win or not, okay, so over here is self dot yeah, self dot win. Okay, if win then end the game. Okay, so maybe self dot done equals to 0. Okay, so actually this I put in reset. Okay, self dot reset like that. Okay, okay, so if self dot win, okay, then what we'll do is self dot done equals to 1. Yeah, then maybe you can have a self dot reward is 1 also. So over here the reward will be 1 if, okay, self dot reward will be like self dot turn. Okay, maybe we have the turn as 1 and minus 1, then we can straight away like get a reward if it's, so the turn could be like 1, and then the next player's turn will be self dot turn times minus one. Yeah, so one for player one and minus one for player two. And then the reward will just be the self dot turn, okay, when it ends. Okay, which also means that no, actually the the player that it ends would be the player that takes the last match take, isn't it? So this one will be times minus one. Okay, define win. Or actually, in this case, this is a loss. Define lose. Okay, over here is you lose when you take the last match take. Okay, so how do you know whether you lose? Okay, so if let's say I have the last match take, okay, which means that self dot match take equals to zero. Just return this. Okay, and then we also need to define something called the we basically define what else do we need to define? We need to define valid moves. Yes, valid moves. So in order to check which is valid, okay, we probably will need to uh, yeah, basically valid moves is any move between 1 to k, right? So uh, max or minimum basically k self dot k and self dot match tick. Okay, and this will be the range that we generate. Okay, return list range of this. Yeah, that's a pretty simple way of coding it. Okay, let's see how it works. So nim environment equals to nim. Okay, so maybe over here we set this n to be 21, k to be 3. Okay, like environment equals to nim, and then environment dot valid moves 0, 1, 2. Very good. Okay, so maybe what we'll need to do is we need to mm, probably need to have a function here to clone the environment as well, I guess, or at least return the n and the k. So maybe in this move function here, what we'll need to do is we need to return n and self dot match tick and self dot turn. Okay, this is the state, the environment state. This is the player's turn, and then maybe self dot reward and self dot done. Okay, so what we can do is like that. Wow. Okay, we also do a define sample, okay, where we just randomly sample here. So over here I need to define like that. Oops, numpy. Okay, we did do that. And over here what I'll do is I'll randomly sample. Okay, random sample from list Python. Okay, so we randomly sample one from there. So I guess we could do a numpy random sample. Numpy random sample. Oh no, no. And maybe numpy random choice then. Random sample generated from its elements. Okay, yeah, we'll just do that. Numpy random choice. Self dot valid moves. Okay, this just basically returns a random move. Okay, may not be the best move, but it's just a random move. Okay, so while not done, okay, what we'll do is uh basically check what is the next move. Okay, so environment.sample and then remove this, and then maybe what we can do is matchstick, turn, reward, done, equals to this. Okay, so actually we don't really need this because we can reference the environment.done already over here. So matchstick turn reward done is this. Okay, and then what we can do is we can just like maybe like return matchstick or something. No, print matchstick. Okay, so we want to actually get the move, right? So we cannot need this to be outside. So we just do this. We print the matchstick and the move. Okay. Uh, player turn player will be, okay, let's just do an F string. Okay, player turn. Okay, so okay, so actually in this case, since we are doing like that, maybe we just have turn as 1 and 2. So here will be 3 minus self dot turn. 1 for player 1, 2 for player 2, and then the reward will be 1 if self dot player equals to 2, else minus 1. The reward will be based on which player it is. Okay, so this will be like that. And you can try this out. Matchstick turn reward done is environment.move, and then we just print out this player turn matchstick comma move, which means this player's turn. Uh, we have player takes how many matchsticks? There are how many matchsticks left? Yeah, we can do like that. Yeah. Okay, we are missing one requirement, num. Oh, okay, I forgot to put the move in here. Okay, so maybe there's something wrong with the move that we printed out. Move 0. Okay, so this valid moves here, I probably need to make the range be like that, +1. K is not defined. Hashtag turn reward done. Cannot unpack non-iterable non-type object. Okay. I guess if there's an invalid move, then this will happen. Okay, we can also print out what is the move so that we know what was chosen. 3 is an invalid move. Okay, why? Player none takes 3 matchsticks. Somehow it seems like I'm getting invalid moves quite often. So okay, this is because this is smaller equals. Okay, let's see. Player 2 takes 2 matchsticks. Okay. Okay, so we should start from player 2. Player 1 takes 1 matchstick. Okay. There are how many matchsticks remaining? Player 1 takes 1 matchstick, 20. Takes 2, there are 18, 16, 15, 12, 11, 9, 8, 7. Okay. And then maybe at the end, we just print who loses. Huh? Okay. So maybe print Okay, name object has no attribute player. Okay, it should be self dot turn. Huh? Player two wins. Okay, so when player two, it should be the other player that wins. So okay, so what we do is if win player player win equals to one if environment dot reward. Okay, so we can see who wins like that. So player one wins because player two took the last match take, so player one won. So yeah, we can do this here like that. Okay, I think we got the game working. So we can see who wins. Player one wins. Player two wins. Okay, so what we can do is we can define this as a game. Okay, like that. And then basically what we want to do is we just want to feed in. Okay, every time when we have this thing here, instead of environment dot sample, okay, we can just feed in the agent over here. So uh, agent n and k. So if we want to fit in the name n and k, then this will be here n and k. Okay, okay. So this plays a game. Okay, okay. This basically plays a game. Agent one and agent two. So we can have agent one and agent two. Okay, to see like what agent is better, and then we have n and k, which is the inputs will be agent one program to make move for player one. Okay, we do the same thing for agent two like that. Agent two program to make the move for player two. N is the number of matchsticks at the beginning, and K is the number of matchsticks upper limit to select to remove each turn. Okay, so these are the input, and then maybe boss will be whether to print out the game. Okay, so these are what we have here. So we have the environment name here. If the environment is not done, then we will sample. Okay, here we need to change. Okay, if environment turn equals to one. Okay, if it's player one's turn, then we do. Okay, so because the state is n and k, so we will give this to agent one. Else move equals to agent two. So we don't do this sample anymore. Okay, here if the boss. Okay, then we print this. Okay, and then over here what we do is we just return the reward. Okay, so this will be the game function. And then for Monte Carlo, okay, we just maybe before we do the Monte Carlo, we just define a random agent. Okay, that takes in the two samples like that. Or actually what we do is we can pass it the environment. We can pass it this environment here. Or maybe what we need to do is just pass it the n and k, and then like the valid moves, I guess. Yeah, so I guess what we really want to do is we just want to do the valid moves. So okay, so what we do is we'll just return np.random.choice self.valid moves. Valid moves. Yep, like that. So this random agent just basically returns a random move. Okay, that's the random agent. Okay, so let's just play a game. Okay, between random agent 21 3. Okay, you see what happens. Okay, missing one, I think valid moves. Okay, uh, I forgot to run this code. Is it? Okay, yeah, that's good. Okay, so you can see that we have an agent that basically performs randomly for both the front and the back, and you can like we can just run this many times. So like it goes false. So we can just okay. Let me shift this up here. Okay, run the game with random agents 100 times to see the outcome. So for I game for num or for game num in okay for game num in range 100, we run this game function, and then we can actually just take like maybe the first the reward will be the players win or not, right? So we can just take like p1 win equals to p2 win. This both will start with 0. Okay, and then like reward will be this. Okay, if reward okay, so if reward okay, actually we can just define this thing over here, like define many games, right? Define tournament. Okay, so num game agent 1 agent 2 and k. In a tournament, maybe our verbose is always false. Okay, we don't need to set this variable. So we can do this n and k. Okay. Okay, let me just copy and paste this thing here. So the tournament will basically displace a tournament with agent 1 and 2, and then n like that. Okay, we have a verbose here. Okay, num games will be like the number of games for the tournament. Okay, like that. Agent 1 like that. P1 win, P2 win. For game num in this range, reward equals to this. Okay, per boss will be false. Okay, this is alright. So I'll be agent 1 and agent 2. Okay, if the reward is 1, okay, then it means that P1 win plus equals to 1. That means like we add 1 win, else P2 win. Okay, and then what we do is we'll just print out. Okay, maybe we do one of our boss. Actually, no, we can just print it out. Yeah, print out um, f string again. Okay, player 1 wins how many, which is P1 win, and then player 2 wins this number of games. Player 2 wins this number of games. Okay, then we can just like maybe run the tournament 100 games, random agent, and 21 3. So you can see that with random agents, they kind of win about the same amount of times. Yeah, they kind of win about the same amount of times, which is what is expected. So let's try to do a Monte Carlo agent, okay, where basically a Monte Carlo agent, uh, this agent will try out all the next possible moves. Agent will try out all the next possible, all the, will first do a move, okay, and then randomly play out the rest. Will do all do each possible move one. Okay, the move with the highest average value will be chosen. Okay, so what we'll do it like that. Okay, we'll do this. Okay, define a Monte Carlo agent. Okay, and then this Monte Carlo agent will basically take in the number of moves to play. So like or rather the number of rollouts. So rollouts will be like 100. Okay, so the agent will receive n, k, and this. So looks like we can't really define the rollouts here because we need to define it in this format. Yeah, unless we do like a wrapper for it, but it's okay. It's too complicated to do a wrapper. We can just use this format and k valid moves. Okay, I mean, if you want to do a wrapper, it will be outside, but no, we don't need to do that. We can just do like rollouts equals to 100. We can change this value later. So what we'll do is, okay, for each in this valid moves, we need to step. Okay, so we need to do an environment. So environment equals to this nim and k, right? We define the nim environment like that. Okay, and then what we'll do is we will just like step through each of the valid moves that is in this environment. So mm, for each, okay, so we have like the value is a dictionary, so we can have like value move. Okay, for I in, okay, so maybe we have the total reward as 0. Okay, and then we just add up the reward here. So we want to play the game like randomly after this move and return the rollout. So actually we can just use this game function here. Yep. So for this, what we can do is we can just do like game. Okay. I know it's weird because we're calling this agent again, but we actually just need the random agent to play through the game. So maybe what I can do is I can do like a function for like, we can do a function random rollout, and then this will basically just call game. Okay, random agent and k verbose equals to false. This will basically returns the reward of a random playthrough, and we can use this method to do the random playthrough because we can just call the random route function. Okay, so over here for this in range route, we can just do random route total reward plus equals to this random route. Okay, and then what we can do is we can just compare the total reward later. So at the end here we can just do like value move equals to total reward divided by rollouts, because that's the number of routes. Okay, and maybe we can just do like print the value. Okay, so we are done. We can just do the Monte Carlo agent now. Actually, we don't need the environment here because we do it in the random route. Let's see again. Random route missing two values, n and k. So you can see that 1 is 0.08, this is minus 0.1, and this is 0.06. Let's see whether they can increase the route to like 10,000. See whether, okay, it might take a while to do the rollout because there's a lot of games being run. So maybe 1,000 games. Okay, 100 is too much. 10,000 was too much. Okay, so you can see that in this game, it seems that 2 is the best move. Yeah, so actually, if you do the number theoretic thing, like if the first player should play, like first you should do like 3 plus 1, which is 4. So the first player should actually pick it such that it will be multiple of 4 plus 1. So the first player should make it 16 plus 1, which is 17 actually. So slightly wrong here, okay, because it chooses 2. So it means that just with 1,000 rollouts is not good enough. It looks like it values 2 quite a lot. Okay, the correct answer for player 1, if player 1 wants to win, player 1 will need to pick. Well, actually, regardless of what player 1 chooses, player 1 actually loses because 21 is actually a number where player 1 would lose. So yeah, I don't blame the AI for making this decision. But if let's say 22, it should pick 1. And yeah, it looks like it is picking 1. Without, okay, this no. It looks like a good proportion of the time the Monte Carlo agent is doing his job and picking 1, I hope. Okay, so I mean we can try it 10,000, see how long it takes to do this. Yep. Let's see how much this. Oh, thanks for the subscribe, by the way. Yeah. So yeah, I'm actually trying to do more like reinforcement learning stuff nowadays, so you can catch me doing it soon. Next up will be like some deep Q network stuff. Yeah. So yeah, this is a very simple game of NIM, and basically I just want to see like how this Monte Carlo thing would work. Okay, so it looks like it's not doing it that well most of the time because maybe it just has too much of a game tree to search through for the rest of the game. Yeah, but seems pretty good. It knows to pick the first action, and okay, no, actually this it picks action 2 instead. So it needs to let it be such that it is a multiple of 4 plus 1 in order to win this game. Okay, to not beat. So I think it's doing pretty okay for now. But let's try something. We just try like 5. Okay, because if it's 5, that means like if you are player 1 and you want to win the game, you need to pick 1 so that it makes the number for no 6. Okay, then you need to pick 1 to make this number of matchsticks left 5. Then no matter what player 2 does, you can just make the number 4. Then the player 2 will be forced to take the last one. So this, if Monte Carlo agent is right, it should pick 1 actually. So okay, is it picking 1? Okay, it doesn't look like it's picking 1, is it? It's like it's okay, let's try 10,000. It shouldn't be picking a value that is not 1 actually. 1 is the best move. So okay, it turns out that this game of NIM is already so complicated that Monte Carlo doesn't scale that well. It's supposed to pick 1, but you see it ends up picking like 2 or something. I mean, let's try an even more obvious example. Like if let's say we have 2, and then maybe the value moves are just 1 and 2. It's supposed to pick 1. If not, it will lose the game. So, yeah, why do I end up with this? This is so weird. Okay, I think I know why. Okay, I forgot to minus move here. Okay, because if I don't minus the move, then this number will be wrong. So what we need to do is we need to minus this move as though I take the move already. Because now all this tree looks like it's doing the same thing. So I need to minus this move here. Okay. And then I need to like minus equals to this because this will be the roll out of the other player. Okay, let's try this again. Yeah, so I guess if this one, okay, return -1. Yeah, so we still want to do a random route, and then the route will just be playing this game until it ends. Okay, yeah, there's something wrong. It's not so I'll give like one here, so I might have done this wrongly. Ah, there we go, there we go. Yep. Ah, okay, good. So when one, you always win, correct? So it means that when this returns one, okay, it means that if I were to take the last tick, I lose. Okay. If not, then we will play the game from the second player's perspective. Okay, and then we will see what reward we get. So let's say if we take three, okay, and then over here, so I need to pick two for certain for an assured victory. Okay, if I pick one, okay, it'll be half half. Sometimes I win, sometimes I lose. If I pick three, I'll always lose. So looks like this is it looks like it's working. So if I try four, the Monte Carlo agent should give me uh it should be, oh yeah, I should be able to pick three. Okay, because three will make me win. So it does look like it has some it is doing some thinking right now. Five, I should pick actually one. Okay, if I want to win, I should no five. I should pick nothing. Okay, actually five is a losing move, so it doesn't matter how you play it. Okay, either way you will lose. Okay, and yeah, it means that you are in a bad position actually. If five, how about six? Six, I should pick one in order to win. Yeah, looks like it's working. Okay, it looks like it's working. Okay, how about 21? Okay, 21, I should pick one actually. 21, I should pick one. The first player can win by picking one. Okay, so it looks like it's not able to really work out that long search because the depth is just too large for this Monte Carlo agent. But let's see if I increase the number of routes whether it's possible. Yeah, so let's try doing this. Uh, okay. Yeah, it does work if I increase the routes for this game because it's like a slightly easier version, I guess. Okay, okay. So if a row is 10,000, it works. Okay, but we just want to make it a row of 1,000 now because we don't want the agent to take so long to decide. Okay, so it may not be optimal, but it should be optimal most cases. Okay, so what we should do now is we should just like maybe run the game between Monte Carlo agent or run a tournament between the okay Monte Carlo agent versus Monte Carlo agent. Okay, and then N and K will be 21 3. Okay, so we can do this tournament now. Int and none type. Okay, is there a none type anywhere? Oh, I actually did not choose my move yet. So what I should do is I should choose the move. So what I can do is like that. I should have like a best move is 0, best value equals to 0 to maybe -2. Yeah, that's the average. So for this move in okay if let's say the move, if total reward, okay, greater than best move, okay, what I'll do is I will total reward greater than best value. Okay, maybe this one I'll just do a very large value. Okay, best value equals to total reward, and then best move equals to move. And then what we do is we can just return the move here, because after all we need to sort of like return our best move, right? And the best move, okay, will by default be 0, so that it will be invalid if we fail to actually get the best move. So let's see. We play a total of 100 games in the with the Monte Carlo agent, and we see whether it works. Okay, so it's taking a while. It takes about, I think, zero point 0.4 seconds to run the games, to make a decision. So maybe it takes a while for 100 games to be played out. Yeah, but not to worry. I think it should work soon. Okay, maybe I can reduce the number of games and see what happens. But if let's say both of them play perfectly, the first player should always win, because the first player is the one that can actually force the second player into a situation whereby the number of matchsticks is a multiple of 4. And then regardless what move the next player makes, you can always make another move to make that sum of those two moves become 4. And by doing that, you can ensure that you will win. So yeah, the moment the game has is at a multiple of 4, okay, the player who moves first would win. I think, yeah, the player if it's at a multiple of 4, the player who moves first will win. Yeah, the aim is to get your move to be a okay, let me think about it. Okay, so if we have 4 matchsticks left, okay, I just need to pick 3 to win, right? Because the other player will win. So if I have 5 matchsticks, I want to pick to 4. Okay, pick 1 so that it goes to 4. No, I should pick 2. Actually, if you have 5 matchsticks, you lose. Okay, so if you are in this situation, you want to be in a situation whereby you don't get this thing. So this one is a lost case. So if you are in like 5 matchsticks, you should do until 5. Yeah, because then when it's at 5, no matter what the person does, you can always, yeah. So the idea is to give the opponent a 4n plus 1 in terms of the number of matchsticks. So the starting player is actually the losing player. Yeah, starting player is the losing player. Okay, let's maybe do 1. Yeah, just to see how long it takes for one game. Oh wow, it takes so long. I didn't expect it. I mean, it's just one game, right? Oh, there's an error with this, because I did not change this to num game. So let's try again. It's just one game. Let's see how long it takes for the game to play. Oh wow, it's still taking so long. Okay, so player 2 won. Okay, so maybe we try 10 games, or maybe the rollouts are just too much. We can try 100 rollouts instead of 1000 rollouts. I mean, just to make the thing faster. Yeah, it's taking a bit long to run the tournament. Yeah. Okay, so it looks like player 2 indeed is winning more than more often than not. Okay, so maybe what I'll do is I'll train this for other tournaments as well. Okay, so it's 5-5. Okay, so let's suppose the random agent is the first one, and the next one we put the random agent at the back. And then we see who wins for those tournaments. Okay, so you can see that there's a bit of a, okay, so the first player wins, which is weird. Okay, it's supposed to be second player that wins. So this Raw obviously is not enough. Okay, so here wins 7 games. Let's try a row of 1,000. Then we see what happens. Yeah. So if we have more rollouts, we should increase the accuracy of our gauge of the value of that state. So we can try that. So a pure naive Monte Carlo approach doesn't seem to be doing too great when it comes to a game that has like potentially high amounts of state search. Okay, and yeah, this may be something that I mean I know deep Q networks can work for this NIM game pretty well. Not I mean still not the best. I mean it still takes a while to train, but it works pretty well. But yeah, Monte Carlo will take very long if it's just pure naive Monte Carlo like that. Probably need to combine it with Monte Carlo Tree Search in order to do better. So I'm just waiting for the agent to finish running. Yeah, sure taking a while. Yeah, maybe 1,000 rollouts was too much for this thing to handle. I mean, I still need to define all this here. I wonder if there's a way to, if you do dynamic programming, actually you can probably solve this game with dynamic programming. Actually, you don't even need reinforcement learning. You can just do dynamic programming. You have a state and an action, and then basically at each state you can store the value of who wins. Yeah, from that state. So I think you can solve the game of name with dynamic programming. You can just like look from the last matchstick state, and then you look backwards, add in the matchsticks. Mm. Okay, let's see why is this not working. Okay, why is this not working? Okay, this is Monte Carlo agent and a Monte Carlo agent. This should it is working. It's just taking very long. Okay, stop. Okay, let's just see the game between them for this. No wonder it takes long because the numbers are huge. This one game takes like that. So you can see when player two wins, output is -1. So the last player one took the last match take. So it turns out that it's not exactly doing the 3+1 strategy yet. You see, it's like 3-2-2, 3-2-2. It's like still a little random. Okay, but towards the end, this player plays perfectly. This one, he took the right match take. And over here, two takes two match takes. Player one takes two. This is a wrong move actually. Yeah, this one here. Actually, when player one reaches here, he's dead already. So no, actually, when player one reaches here, this is worrying. Okay, he's supposed to take three match takes for player one because then he makes the number of match takes left three. Okay, which is very funny why he did not do that. Okay, let's try again with four. You see, it always does like that. Okay, how about seven? Yeah, it's a bit funny why they don't do the same strategy because like if it's four, the first player knows what to do. Always takes three, right? But if it's like five, it can sometimes be like a bit weird. Okay, let's try with more rollouts. Maybe not enough rollouts for no. It should be one match takes actually. It's so weird. I mean, this is a very simple problem, is it? See why did they take two? So the Monte Carlo agent is not exactly doing okay. It's a bit funny that it like kills itself here. We need to solve this problem. Okay, this is an issue with the AI. The player two shouldn't take two matchsticks. The player two should just take one matchstick here. But you see, if I do here two, they know. Okay, if I do three, they know also. So if I do four, they know also. But it seems that once we do like five, the no longer does what it's supposed to do anymore. Because the first player should. Okay, this is still okay because player one is in a losing state. But if it's at six, the first player should make it five. Okay, okay. So it's not that it doesn't know what to do, it's just that it is in a losing state. So yeah, this is weird. This player one over here. See, there's three matchsticks remaining. Why don't they just take more than one? Yeah, this player two move is okay. Player one should make it like so weird. I mean, it seems to think that one is the correct move when it's not. Yeah, there's something wrong with this. Okay. So let's just do some debugging. Okay. Oh, somehow it only has one. Okay, okay. So the issue is not the rollout. The issue is valid moves. Oh, okay. No, no, no. It's not. It's not. The issue is not the valid moves. It's just that I did not print out everything. Okay, so one matchstick is correct. Okay, this part here, he's supposed to take three matchsticks to end the game. I think I know why. I think player two is not playing properly because the reward function is different for player two. So for player two, because the game's reward at the end of it will basically be this Monte Carlo agent doesn't know whether it's player one or player two. Okay, so it could be that because whenever you look at player one looks like he's taking the right move all the time. So like player one plus one. Actually, not really. Player one did not take the right move here. So I'll take two. Two is the most negative. Yeah, this is very funny. Yeah, there's some problem with this Monte Carlo agent here. Think about how to solve this. Maybe I need to give it the player turn. Yeah. Hello, Joshua. You can come here. Yeah, he's trying to code a game here. Yeah, somehow it's not working. Yeah. So let's see what we can do about this. Oh, oops. All right. Let's try to do it in the next 5 minutes. Okay, I probably have to go soon. Okay. Let's try to solve this Monte Carlo agent before I leave. Okay. Uh, okay. Somehow it's not getting the right match stick. Okay. Player one is okay. Player two. Okay. This is the problem. Player two. Somehow it doesn't seem to give. I guess if I were to use a random roll out like that, there could be a case that uh that the other player just does something nice, and then yeah, if the other player does something nice, then your that move could actually be a good move. Yeah, if we were to just assume that both players play randomly, so maybe that's the issue. Yeah, but I have to assume that they are all random agents though. Yeah, because yeah, maybe that's the downside of this Monte Carlo agent. In this case, where there's an adversary, it could be very well that it does not uh they don't play perfectly. Okay, because of the nature of this random rocks, and then you just don't get the right approach. It's very funny. I thought it should play perfectly because, like, if let's say there's like four matchsticks remain or five matchsticks remaining, it should always pick one because it knows that no matter how the other player chooses, it will work. Okay, but now that it reaches until like four, it doesn't know how to do the next move. I mean, there are ways to do it the next move. Like here is still not too bad. But why is it only like 0.004 for this? There's some problem with this move three. Okay, because this should give us like a value of one. So okay, I know how to try to fix this. We try 4 3. Okay, the move three should be like a one. Okay, so this is correct. Okay, so this is okay. How about a seven? Okay, two is correct. So you see, it does work for player one like that. Yeah, this looks okay. All right, this looks like a perfect play. Yeah, and player one knows what to do. Okay, player one knows what to do. This player two has no choice. Okay, so this does look like it's playing perfectly. So we can see. Okay, there's some issue here. You see, this move two is giving a value of 0.107. Okay, it's not supposed to give us this way. Okay, it's supposed to be a flat out one. You are supposed to win all the time. So maybe this part here is wrong. Random roll n minus move. So this one is if n is 0, return 1. Okay, okay, maybe I should add something here like if n equals to 1, return minus 1. Okay, if it's 0, the player loses. Okay, if it's 1, the player wins. Okay, if not, we play the game. Yeah, somehow turns out that this game here, maybe we should debug this part here. If let's say it's a 1 3, what will happen? -1, right? Yeah, so it turns out that it's 2, 3 is also -1. Actually, 2, 3 can be 1 also. Depends on how you play it. But 1, 3 is definitely -1. So it looks like this is correct. Yeah, I'm not sure whether this would help it, but let's try it. So this part here still looks okay. So it means that we already subtracted away. Okay, this is funny. This is funny. Yeah, this such it isn't supposed to give us this number here, unless I did something wrong here. So I give 1 and -1, right, for my reward. Yeah, maybe the issue is if I count the total reward, it sort of. Oh, is it? No, I mean, I'm supposed to win all the time, right? If I take move two, I'm supposed to win all the time. Okay, but they only won like 1182 games. I should get this here, and this here should give us all the time. So okay, let me just change this to 1K. Let me just try to debug this. It should give me 1 all the time. So 2, it should give me like, okay, this around there. This is quite accurate. Okay, so if let's say we have a n minus move. Okay, let's just print out the n minus move and the total reward as well. 6, okay, 5, 4, okay. Okay, 1128, 1194. So weird. I mean, this when it reaches this place here, when there's like a total of, oh, do you see that? The state is always 7-3. The state is always 7-3, so this n has not been changed. Ah, no wonder. I was thinking, why is it so hard for the game to play? There's an error in the game function. Oh my gosh. Yeah, I've been giving the agents n all the time, which is a total number. We should be giving the matchstick instead of n. Okay, okay, this should solve the problem already. Okay, so over here, yeah, I was thinking why didn't it go all the time? Okay, it's because it has been given the wrong information. Okay, now it does correctly. Now it does correctly. Is it 5-3-1-1? Yeah, I was thinking this game shouldn't be that tough. Yeah, all right. Okay, so all right. Okay, I think we can remove all the print statements here. Okay, maybe I just see one time just to make sure. 113. Yeah. Okay, so if let's say 21, my Monte Carlo agent should take in terms of like 4, 2, 2, 1, 3. Oh, 3, 1, 3, 1. Okay, so this is a group of 4, groups of 4, groups of 4. Okay, maybe over here it hasn't been able to calculate yet, but definitely when it reaches here, it should give me 1. Yeah. Okay, good. 5-3. Okay, this should give me one. Yep. Okay. Okay, if I do like 10,000 rollouts, I think maybe it might be able to even determine earlier how to do the 1-3 formulation. So yeah, that was a very crucial find. Okay, the crucial finding was that I had given the wrong parameter for my n over here. Okay, because I given it n instead of the batch ticks, which means that um, pretty much it has been given the state of the start of the program rather than the state itself. Okay, so let's see. Okay, so I'm supposed to reach. So player two is trying to. Okay, so player one reaches 16. 16 is actually losing. 16 is actually a winning number. Yeah. So player one knows that if he reaches the number 4n plus 1, no, actually 60 is a losing number. Okay, so assuming 21, if let's say we don't want to be the last one to take the match take, we need to give a multiple of 4 to your opponent. So give a multiple of 4 to your opponent, multiple of 4. Yeah, so actually player 1 is playing perfectly already. You give a multiple of 4 to your opponent, and you can see that it's playing perfectly over here. 2016, and then over here, okay, over here there's a boo boo. Okay, over here so will be 12. So there are some errors in the program's gameplay. Okay, but over here you can see that although there's an error, okay, but this is actually quite close with move 3, so it means that with more simulations it should actually solve this. Okay, I think I'm quite satisfied with this already. Let's just let this run here. Okay, we don't need to print the move anymore. Quite satisfied it's actually working. Okay, let's just do the tournament now. So we can do one game. We can do like tournament. We can try this tournament here. Okay, let's try the tournament now. Okay, I guess I have to continue this stream with Monte Carlo Tree Search another time. Okay, because I have to go already. Okay, but it does look like 1,000 iterations seem to work pretty well. Like you can see that over here is 1-3. Okay, but over here this is wrong. This shouldn't be 2-3. This should be like 2-2. Okay, so yeah, still not the best, not the best, but does look like there's some improvements. Definitely against the random agent, I would expect the Monte Carlo agent to perform well, but it probably isn't the best agent to use right now, because it just takes too long to calculate um, the actual value of the state itself. So yeah, let's just see how this works. Let's give it a while. Yeah, this tournament sure takes a long time, and I already used 1,000 rollouts only per, per move, and it takes so long already. Okay, maybe let's just try like maybe 4 games, because one game shouldn't take too long. Tournament. Okay, let me just try a tournament of one game. Okay, so it'll take as long as the first one. Not there's something wrong with the tournament code. This game didn't take very long, right? It's first game. Okay, so it should take about the same amount of time as that. Okay, so if we like play 4 games, Okay, so it's about half half. Okay, means it's not very like well defined yet. But let's try 10 games against a random agent and we see what happens. Okay, if the Monte Carlo agent is better, the Monte Carlo agent part of it should perform better than the random agent part of it, regardless of where it starts from. So in this game, without any heuristics, Monte Carlo may not be the best bet. Oh, yeah, I just see my Monte Carlo agent getting smashed. Funny, huh? That this one it loses. Let's try something. Somehow it looks like the Monte Carlo agent is not being put. Yeah, it's layer one wins all the time in this. Funny. Let's just print environment.turn here just to see whether it's changing correctly. It's wow. It's like printing 2 1 2 1 2 1 all the time. Okay, it looks like we have to solve this problem later. Okay, I've got to go and yeah, I'll continue this stream again later on. And thanks for viewing and see ya.